Hello, this is Guillermo Campitelli, and in this video we continue with a case in which one nominal variable affects one numerical variable. We've seen parameter estimation approaches in the previous video. In this video we are going to see the model comparison and the hypothesis testing approaches. So starting with model comparison, we have maximum likelihood and Bayes factors. So maximum likelihood first. Basically the models, in terms of causal models, we are going to compare a model in which the only variables that affect happiness are unknown. So basically we are we don't have any variable to predict happiness. Against a model in which the variable of interest, exposure to short films or documentary for short, and is one of the causal variables of happiness, and the other one are unknown. So in terms of the statistical model, we've got these two formulas. First, happiness is distributed normally with mu I and sigma. So mu I means that there is a value mu for each participant, but there is only one sigma for all the participants. So the mu is the prediction of the model, and so basically what we have is 400 values of happiness, and they are going to be predicted using a normal distribution with a mean of mu I. So for each happiness value there will be a prediction mu I, and in maximum likelihood we are going to determine how likely is to obtain that happiness value, and in a distribution, in a normal distribution with mean mu I and some sigma. And the mu I in this case is one parameter called beta 0, and because we are not using any variable to estimate beta 0, the best beta 0 is the mean of happiness. So basically the mu is going to always be the mean of happiness, which is not a very good model to try to predict happiness. So we try to predict with model 1, make a better prediction, and we are using the variable exposure to short films. Now we've seen in previous videos that we use a linear model, but in previous videos we use numerical variables instead of a nominal variable. So here the predictor variables or the independent variable is a nominal. Okay, so there is a trick to solve this problem, because linear models require they don't accept nominal variables, but we can transform the nominal variables into sort of numerical variables, or we call it dummy variables, by doing the following. So for gardening we are going to assign the number 0 for people who were not exposed to gardening, and number 1 to the people who were exposed to gardening. We do the same with poverty and with success. Now notice that we don't need to use it with the 4 categories. This beta 0 would be the mean of the other category. So cooking. So the beta 0 in this case would be the mean of cooking, and then our estimation, our prediction for each participant of happiness is the beta 0, which is the mean for cooking, plus the effect, how much more happiness you expect in comparison to gardening, so when you compare gardening to cooking, the beta 1 is how much you expect, how much more of happiness you expect if you are exposed to gardening in comparison to cooking. Beta 2 is how much more you expect of happiness when you're exposed to poverty in comparison to cooking. And beta 3 is how much more happiness you expect when you're exposed to success in comparison to cooking. Okay, so we have to estimate these parameters to come up with mu's that are as close as possible to the actual values of happiness, and so the likelihood in this normal distribution of each value of happiness is higher. Okay, so I did this with R, and the best beta 0 is 2.197, which is the mean of the whole of the 400 values of happiness, and the AIC is 3994.9, and for model 1 the beta 0 is 4.87, which is the mean for cooking. Beta 1 is 0.06, the extra happiness that you would get for gardening. Beta 3 is minus 54.88, which is the extra happiness that you would get for poverty, which in this case is negative. So you are expected to have 54.8 points less of happiness in poverty in comparison to cooking. And beta 3 is the extra points you would get for being exposed to a successful story in comparison to cooking. And based on those parameters, we calculate the mu's, and we estimate how likely it is to obtain each value of happiness that we actually observed in those normal distributions with mean of mu. And the AIC is much smaller number, 2477.6, so more than 1000 points of difference. So model 1 had received huge support in this model comparison. Okay, so base factor here, as model comparison, we can use JASP very easily, but I'm going to show you the model comparison approach of JASP that JASP uses when I explain hypothesis testing. Because remember that hypothesis testing is a special case of model comparison. So I will show you that later on, but I wanted to show you something that I did with R that you cannot do with any of the traditional analysis. And it's actually a very, very important analysis that I'm going to show you. The typical ANOVA analysis that I'm going to show you in a minute, what determines is whether one of the means is different than the rest. At least one of the means is different than the rest. And that's all. So basically, the model 0 would be the null in the null hypothesis testing approach. Basically, it says that the mean for success is equal to the mean for gardening, and the mean in cooking, and the mean in poverty. So the happiness rating would be the same in each condition. That's the null hypothesis. But what we are going to test in null hypothesis testing is whether this is true or not. And if it is not true, it could be that success is different than gardening, that gardening is different than cooking, cooking different than poverty. It could be that they are all different, but we don't know exactly. This model has a much more specific prediction. It says that the mean for happiness is higher in success than in gardening, higher in gardening than in cooking, and higher in cooking than in poverty. So this is what typically we are interested in. We are interested in knowing the order of the groups, not just whether one is different than the others. And this one is even more interesting because it says So comparing model 1 and model 2 is even more interesting, because this one says, okay, success is higher than, the mean of happiness should be higher in success than in gardening and in cooking, but in gardening and cooking should be the same. And gardening and cooking should be higher than poverty. Okay, no traditional analysis can do anything to test this. Now I'm going to show you one thing that I did in R, and this is not the only way. Actually, there are other possibilities that are, and look at the references in the text. Okay, so what I did is to generate 3 models with different types of priors. And for the model in which all the means are different, so I established 4 distributions, 4 prior distributions, one for success, one for gardening, one for cooking, one for poverty, and they all have a normal, they are all a normal distribution with a mean of 0 and standard deviation of 15. Okay, so the expected value for the 4 categories is 0, but there is a dispersion of 15, so quite large dispersion. So it allows for a large amount of values to be relatively likely. Now, model 1 has 4 different normal distributions. So for success is a normal distribution with 40, a mean of 40 and standard deviation of 15. For gardening, the mean is 25 and standard deviation 15. For cooking, the mean is minus 25 and standard deviation 15. And for poverty, the mean is minus 40 and standard deviation 15. So basically, with the prior, we are doing this hypothesis that success should be higher than gardening, gardening higher than cooking, and cooking higher than poverty. Model 2 implements so the priors that I chose for model 2 also follow this idea. So the mean for success, the prior for success also is a normal distribution with mean 40 and standard deviation 15. Now the means for gardening and cooking are different. Before we have one 25 and the other one minus 25. In this one, the 2 of them have a mean of 0 and standard deviation 15. And the mean for poverty, the prior for poverty has the same mean and standard deviation as in model 1. So again, what we need to find out is, based on the data we obtain, what's the marginal likelihood of each model. So are the values we obtain more likely under model 1, under model 2, or under model 0? Okay, so basically I used the naive Monte Carlo approach, and I calculated the marginal likelihoods for the models, and you can see marginal likelihood for model 0 is 2.9845 e minus 13. Marginal likelihood for model 1 much lower, much higher value, 2.5216 e minus 0.8. So it has less zeros than this one. And the total marginal likelihood for model 2 is 4.0347 e minus 0.7, so a bit larger than that one. So the base factor, we do 3 base factors comparing the 3 marginal likelihoods. So base factor 1, 0 compares model 1 with model 0. It's 84,489, saying that model 1 or the data is 84,489 times more likely under model 1 than under model 0. With model comparison model 2 and model 0, base factor 1,351,630 means that the data is 1.3 millions more likely under model 2 than under model 0, and base factor of 2, 1, comparing model 2 and model 1, is 16, meaning that the data is 16 times more likely under model 2 than under model 1. So let's now move to the hypothesis testing approaches. First NHST and then base factors. So we're going to use JASP for NHST. We use the ANOVA, and basically we continue the analysis that we did. So basically, when we did parameter estimation, we were interested in the post-hoc test and marginal means. But when we do hypothesis testing, we are interested in this table. So basically, we get the sum of squares for the variable, independent variable, the residuals, degrees of freedom, mean square, the f-score, and whether it is significant or not. That's the p-value. So here it is. So basically, this means that the variable documentary affects the happiness ratings. So we reject the null hypothesis. Now I'm going to briefly explain the rationale of the ANOVA. Basically, first you calculate the variability of the whole data. That's the sum of squares total, which is not shown in the table, but you can easily calculate, because the sum of squares total is the sum of squares explained by the variable documentary plus the ones that are not explained. So if you add these two, is the sum of squares total. Then we've got to calculate the variability explained by the model. So that is how much the group means differ from the grand mean. So the grand mean takes into account the 400 values, is the mean of the 400 values. So how much the group means differ from the grand mean. And actually, technically what we do is to assign to each participant the mean of their group. And we subtract the grand mean from that value, and we obtain the square values, and we add all those. So that would be the variability of the whole data that is explained by the model. Now, when you do sum of square total minus the sum of square of the model, then you've got the sum of squares error. Technically, also the sum of square error is you subtract the mean of each group from the actual score of each participant, and then you square that and you add those, and you've got the sum of squares of error, or more precisely, residuals. Okay, so we've got the sum of squares of total, which is the whole variability of the data. We have the sum of squares of the model, which is the total variability that is explained by the model, and the sum of square error or residual, which is the variability that is not explained by the model. And then we calculate the sort of average of those values. We don't need to do it with the total, but we calculate the mean of the square errors and the mean of the squares of the model. So basically, for mean square of the model, we do the sum of square of the model divided the degrees of freedom of the model, which in this case is 3, because we've got 4 groups. The degrees of freedom is 1 less than that, so it's 3. And the mean square error is 396, and that's because the sum of squares total is 399. That is 1 less than the 400 values we obtain. We have, and So we've got 399 this for the sum of square total. But we have to get rid of these 3 or subtract these 3, and we get 396. So the mean square error is what we have to do is the sum of square errors divided the degrees of freedom for error, 396. So we've got the mean square for the model and the mean square for the error. Then we obtain a ratio of those values, and that's what is called the F-score. So we obtain an F-score for our study. And what does it mean? Well, we've got a sampling distribution of F-scores with degrees of freedom, and basically it will tell us, based on the degrees of freedom, what's the probability of obtaining the F-score we obtain in our study, or a more extreme value. If the sample comes from a population in which the mean of the 4 groups are the same. So if that probability is very low, then we reject the null hypothesis and we say, well, this sample didn't come from a population where the means are the same. And if the probability is not so low, then we don't reject the null hypothesis. Okay, so basically here we have, for the model, we've got in documentary, the sum of squares of the model, degrees of freedom of the model, the mean square error, mean square of the model, and same for residual, sum of squares for the residuals, degrees of freedom, and the mean square, and then the ratio of these two is the F-score, and this is a very high value, so the probability of obtaining this value under the null hypothesis is very, very, very slow. And these are effect sizes measures, eta square and partial eta square, which in this case is the same value, and it's sort of the amount of variance that is explained by the model. Finally, I'm going to explain the Bayesian approach to hypothesis testing using Bayes factors, and the software is JASP. Okay, so what we need to do is to go to ANOVA, and instead of going to ANOVA as we did before, we go to Bayesian ANOVA, and we put happiness as dependent variable, documentary as fixed factors, and basically that gives us the Bayes factor. So Bayes factor of 2.395 E plus 322. So a huge evidence in favor of model 1 over model 0. So basically, technically the null model is a model with a spike in 0 for all the betas that I showed in the formula, which is, we have beta 0 for cooking, beta 1 for the extra value of success over cooking, then beta 2 for the extra value of gardening over cooking, and the extra value, beta 3 extra value of poverty over cooking. I might have changed the order, but basically those beta 1, beta 2 and beta 3, they should be 0 if the difference between means in the population is 0. So what the null model does is to put a spike on 0 for beta 1, beta 2, beta 3. And for the alternative model, if we go to advanced options, we see that the prior is a Cauchy distribution with the R scale parameter 0.5. So again, this is like a standard deviation in a normal distribution. That's the default that the author of the base factor package that runs with JASP decided based on a lot of analysis. And so basically it gives a variability with around 0, and but values away from 0 have some probability, whereas the prior for the null model only allows values of beta 0. So that's in the population, but what's the beta we obtain in our sample? Okay, so in the null model, we'll accept that we can get a betas a bit higher than 0, a bit lower than 0. This will still be likely because is this a sample, and by chance we can get a sample in which those parameters are a bit higher than 0. But values away from 0 are very unlikely. Whereas in the alternative models, values that are away from 0 are more likely than in the null model. But and therefore, when you calculate the marginal likelihood of values away from 0, the alternative model will do better than the null. When you calculate the marginal likelihood of values very close to 0, the null will do better than the alternative. Okay, so the values are much is clearly by the descriptives we have that the values should be away from 0, so the base factor is very, very much in favor of the alternative model. Okay, so this is the end of the base factor explanation and both hypothesis testing approaches.